Hey y'all, it's Sarah. We're back with our applications of differentiation portion of the Calculus 1 series, and today we're talking about the mean value theorem. So, first of all, Rolle's theorem is a nice preliminary to this. So basically, if f is a continuous function on a closed interval, and it's differentiable on the open interval that corresponds to that closed interval, and the endpoints of the interval have the same function values, right? So in this graph, f of a is equal to f of b, right? These have the same value. Then there has to exist some value in the interval, in the open version of the interval, where the slope of the function is 0, right? The derivative is 0. So in this graph, it's pretty clear that at this point, the derivative is 0, right? Slope is 0. And at this point, the slope or the derivative is also 0. So here we actually have two different points where this is true, but Rolle's theorem just requires that there's at least one point where this is true, so long as f of a equals f of b. All right, so let's do an example of Rolle's theorem. So we are given this equation, x cubed plus e to the x equals 0, and we want to show that it has exactly one real solution. So we are going to use a proof by contradiction here. So the first thing we're going to do is use the intermediate value theorem to prove that there must be at least one root, one solution, right? And then we're going to use a proof by contradiction using Rolle's theorem to prove that there can only be one. So first, we're just going to define a function. F of x is equal to x cubed plus e to the x. And we want to prove that at least one place, this function is equal to 0. So let's try the interval 0, 1. Or sorry, we're going to do -1 to 0. Yeah. So let's plug in -1 and 0 and see what we get. So f of -1 is -1 cubed plus e to the -1. That's -1 plus 1 over e. E is 2.718. It's, that's close to a half. So basically, this is going to come out to being something negative. And then we plug in 0. We get 0 cubed plus e to the 0, which is just 1. And so that is greater than 0. So, okay, this function is continuous, right? X cubed is continuous, e to the x is continuous, so the whole thing's continuous. It's also differentiable because both x cubed and e to the x are differentiable, so the IVT applies. So, based off of this fact, by the intermediate value theorem, there exists some c in the interval from -1 to 0, such that f of c equals 0, right? So what that means is that x cubed plus e to the x equals 0 has at least one real solution, right? Because it definitely has a solution between -1 and 0, so it has to have at least one real solution in general. Now we're going to prove that there can only be one. So we're going to suppose for contradiction that this function has two solutions, A and B. And we're going to suppose without loss of generality. So basically, that just means that we could have done this either way. We're just picking this way, and it doesn't make a difference. We're going to let A be less than B. Now, we know that f of A equals 0 and f of B equals 0 because they're both solutions to this equation, right? They're both roots of f. So that means that f of A equals f of B equals 0, right? So f of A equals f of B, so we can apply Rolle's theorem. So by Rolle's theorem, there's going to be some number in this interval. So we're going to call it D. Such that f prime of D equals 0. However, let's actually take the derivative of this function, right? If f is x cubed plus e to the x, then f prime is 3x squared plus e to the x. Now, if we plug in any different x value, any x value that's a real number, this is always going to be positive, right? Because 3x squared is always positive except at 0, and then e to the x is always positive. And so this is greater than 0 for all real x. And so this contradicts the existence of a solution D such that f prime of D equals 0. So right, it's impossible that f prime of D equals 0 if f prime of anything is greater than 0. That's a contradiction. And so based off that, it's impossible for there to be two solutions A and B, right? There can only be one solution. So that's the idea of a proof by contradiction using Rolle's theorem. Next, we're going to get into the mean value theorem. So again, we're starting with a continuous function on a closed interval that's differentiable on the corresponding open interval. And what we're saying now, so we're not going with the same assumption that f of a equals f of b, right? Now we're just saying that there exists some number in the open interval such that the derivative of the function at that number is equal to f of b minus f of a over b minus a. Notice that f of b minus f of a over b minus a is just the slope of the line between the 2 points, right? So if we draw a line between f of a and f of b, the slope is going to be this. Okay, so if we move this line here, okay, right around there, at this point, it seems like that's the tangent line, right? And there's actually another point here where that works. If we draw the line between A and B, move it here, at this point here, the slope is going to be the same as that line. So that's sort of the visual aspect of the mean value theorem. So we're going to do an example of how to apply the mean value theorem. We're trying to show that the absolute value of sine A minus sine B is less than or equal to the absolute value of A minus B for all A and all B. So what I'm going to do is define a function, f of x equals sine of x, right? So in this case, f prime of x is going to be cosine of x. So let's look at what the mean value theorem, or MVT, requires. So if f is continuous on the closed interval and differentiable on the open interval, then there's some number where this applies. So f of x equals sine x is actually continuous and differentiable everywhere, right? So by the mean value theorem, there has to be some c in AB such that cosine of c, so f prime of c, equals sine of b minus sine of a over b minus a, right? So for any a, b, this is true because sine of x is continuous and differentiable everywhere. So we can make this general. And this is by MVT. Now, just based off the range of the cosine function, we know that the absolute value of the cosine of anything, here it's the cosine of c, is less than or equal to 1. Okay, and we know that cosine of c is equal to this, so let's sub in this fraction for cosine. So now we have the absolute value of sine of b minus sine of a over b minus a is less than or equal to 1. Now we can separate out the absolute value so that it's the absolute value of sine b minus sine a over the absolute value of b minus a, and multiply both sides with the absolute value of b minus a. So we get the sine of b minus the sine of a, all in absolute value, is less than or equal to the absolute value of b minus a, which is what we were trying to prove in the first place. So a lot of the problems that you're going to see on both Rolle's theorem and the mean value theorem are going to be sort of proof-based, and so they're going to require this sort of familiarity with, proofs by contradiction, like what we did up here, and then with just sort of being able to, guess and check different approaches until you find a proof that works. Basically, with writing proofs, I typically write multiple drafts. Even today as a grad student, especially today as a grad student, oftentimes, there will be 5 drafts, 5 different ideas for ways to approach a problem before I find something that sticks. So keep that in mind when you're solving these types of problems. Anyway, if you enjoyed this video, please like and subscribe, and I'll see y'all next time.